Welcome to today's webinar about the classification tree method. My name is Roland Bickel. Please let me shortly introduce Hitex to you before our text expert Frank Büchner will explain the advantages of the classification tree method. Hitex was established in 1976 as an embedded development company and has achieved rapid growth by developing and providing microcontroller development tools. Today, Hitex, as a proven expert, is also in great demand as a service provider for training and consulting, test services, development and production services. Hitex supports all phases of your project from the idea to the finished system. For many years, Hitex has been an expert for software quality, functional safety and certification issues, with a great number of successful projects. In our recent webinars, you have learned about the theory of unit tests and the basic operation of TESSY. Today, we will introduce you to the classification tree method and how this method can be used to efficiently define the right test cases. During the webinar, you will have the opportunity to ask your questions via the webinar panel. For this, just click on the orange button with the white arrow in it. We will try to answer your questions during the webinar. Otherwise, we will send you an email afterwards. And now enjoy our webinar. Please take over, Frank.
Yeah, thank you, Roland, and also warm welcome from my side to the webinar. I would like to start by giving you an overview of the topics we will handle in the next 60 minutes. I will start with some question, what is point one, and then in the second and third point, which will be the emphasis of this webinar, in the second point I will introduce you to the classification method, to the theory of the method, and then we will see how this method is applied to an example, the ubiquitous value and range example. After that, I will give you a short live presentation on how the tool which supports the classification tree method, a tool named CTE, which is an abbreviation for classification tree editor, how this tool is integrated with TESSY. TESSY is, as you might know, a tool for automated unit and module testing of embedded software. After that, I will give you a quick look in the testing process. A proposal about the testing process could be defined by using this method and the tool TESSY, just a proposal, but it solves, or it answers, solves the problem, gives a solution for the problem that the developer itself should not be testing. And in the sixth point, we will have some enhancements to the method, some tips, tricks, hints, and in the last point, we will have a short conclusion on everything. Okay, let's start with what it's all about. Today, we're talking about test case design or test case specification, and this handles the question like how many test cases do I need? If I know how many test cases I should have, which test data should I use for these test cases, and how do I manage to generate error-sensitive test cases? An error-sensitive test case is a test case which gives me, which reveals an error with a high probability, which is opposite to redundant test cases, which that does not add much to my insight in the testing. And also problem is, do I have overlooked some test cases or not? And if I can answer all these questions, eventually I can also answer the last question here, when it is safe to end testing. And this means the method or the test case design, the test case specification also gives you an indication when you should stop your testing. Okay, the answer to all these questions might be given by the method I would like to introduce today, the classification tree method. And in one sentence, the classification tree method transforms a functional problem specification into a set of test case specifications. I do explicitly say test case specification and not test cases, and we will see the difference later on. The classification tree method stems from Daimler, back from a time when were called Mercedes-Benz. Okay, this was the introduction. I hope you are interested. Further on, let's go to the classification tree method. First, I would give you a short view on the features of this method. First of all, it's a general method. This means even if I introduce it here together with a unit testing tool, it's a general method and you can apply it to system testing as well as to unit testing. A prerequisite for applying this method is only that you have a functional problem specification of your test object, a functional specification, which means you need to know how your test object shall behave. The big advantage of this method is it creates intuitive, understandable results. So it's very easy for someone to understand how many tests you have specified and what each test will test and why each test is there. It is easy to learn. You need to learn it because it is a method which is applied by a human being. It's not a completely automatic or a software tool that acts completely automatic, but you need a user which applies this method, and yeah, this user should be familiar with the problem at hand. But if you have such a user, this method encourages the creativeness of the user because it is a systematic method, and systemacy means you are looking in every corner of the problem to find good test cases. Systematic does not mean deterministic. This means if two persons would apply this method to the same functional problem, you have a high probability that both persons will find different sets of test case specifications. This, so it depends on the user, on how it rates, on how the user rates some items, and yeah, so it does not exist the correct solution. Okay, next is the steps in which this method is applied. The first step here is called identify test relevant aspects. This, yeah, and you could ask what the hell is a test relevant aspect, and I would like to say it in my words. A test relevant aspect is something you want to variate during the testing, and it's not so easy sometimes to find out what is a test relevant aspect and what not. Think of a distance measurement equipment or a tool which measures, for instance, a distance between you and the wall or something like that, and think of such a tool, such a product which uses different physical means to determine the distance, and if you think of a tool that uses, for instance, sonar, and another one which uses radar, and the question is the temperature of the air between you and the wall, is this a test relevant aspect for the test of such a equipment, yes or no? So it depends on the physical means, and as you see here, if the device uses sonar, you should do tests at different temperatures, because the velocity of sound in air depends on the temperature of the air, and on the other hand, if you have a device that uses radar, the temperature is not relevant because it's not a test relevant aspect, because because radar does not depend on the air temperature. It is always the speed of light, and it will not change. So the first step in applying this method is you make a list of all the test relevant aspects that you can think of, and the second step then is you think about the values of such test relevant aspects can take. And sometimes you are lucky, and such a test relevant aspect can only have 2 or 3 distinct values. For instance, if you think of a switch which can only have 3 values, then you are lucky because you can use all these 3 possible values of this switch during testing and combine it with other input values or with other values of test relevant aspects. But sometimes you will find out that your test relevant aspect can take a very, very huge amount of possible values. And especially if you have other test relevant aspects which also can take a huge amount of values, and you are going to combine every possible value of one aspect with every possible value of the other aspect, so you will quickly find out that you get much too many test cases, a huge amount of test cases, which is called a combinatory explosion. And and if this should be the case, the method, the classification tree method suggests to apply something which is called equivalent partitioning to come to a smaller amount of test cases. And equivalent partitioning works like that you create classes for the values of your test relevant aspect, and you put all these values in one class, of which you think that if one value will find an error in the test object, all the other values in the same class will also detect the same error. And this means you are able to select an arbitrary representant from one class and use this value for all the tests you plan to do. And this reduces the amount of possible test cases to a very very small extent. And but the problem of the method is you are the one which creates the classes, and if you make an error in this, that means if you do 2 values in one class of where one value will detect an error and the other value will not detect this error, and then you pick up the wrong value from the class for testing, that's not good. So please design these classes carefully. I will make an example for such an equivalence partitioning thing. Let's think of the dashboard of a car. In the dashboard of a car, often there is an ice warning indication which blinks or something like that if the outside temperature falls below 3 degrees Celsius. And if your task would be to test such a ice warning device, and you have a specification which says, okay, between 3 and 80 degrees Celsius, the ice warning should be off, and between -60 and +3 degrees Celsius, the ice warning should be on. You could come to an equivalence partitioning which looks like this. You see here the division in classes. First I have made a green class which covers also values between 3 degrees and 80 degrees, and I have made a yellow class which covers also values between -60 degrees and +3 degrees. What is new, and which was not introduced by the functional specification, are the 2 red classes on the left hand side and on the right hand side. They stem from the assumption that there could be invalid values in our example, which maybe stem from a defect sensor or from a broken cable or something like that. And if you do such an equivalence partitioning, you should always think about, are there possible invalid values, and if yes, you should create classes, 1 or 2 or more classes for these invalid values. This will assure later on that you have test cases using these invalid values, what is very important to have such test cases. Okay, I'm by myself not really satisfied with the equivalence partitioning I have made for this example. And what is my critique at this equivalence partitioning you see here is that I would be able, according to the rules, to pick just one value out of a class and perform all the tests with this value. This would mean I would be able to pick out, for instance, a value like +2 degrees from the yellow class and perform all the tests with this value. And this would mean, on the other hand, I never would have a value from this area of the yellow class with minus temperatures, and to check that the ice warning is on at minus temperatures. And if you are not really satisfied with your equivalence partitioning, you are able to iterate this equivalent partitioning, what I have done in the following step, and what you will see on the following page. I have divided the yellow class into two other classes. One class where the ice warning is on at minus temperatures, which is depicted here, and the other class where the ice warning is on at plus temperatures. This iteration guarantees that I will have test cases later from each of these classes, so I will be sure that I will test my ice warning implementation at minus temperatures. Okay. That's about equivalence partitioning, and the first step in applying the classification tree method is to make equivalence partitioning for all of your test relevance aspects, maybe iterating this equivalence partitioning, and the result of this first step is a tree, the so-called classification tree, and the classification tree for this example here would look like that. The root of the tree is at the top. This means the tree grows from top to bottom. At the top is the problem ice warning, and in this rectangle here with the solid borders, there is the test relevant aspect we have found for this problem, and this is divided in two classes. The test relevant aspect is the temperature, of course, or values which correspond to temperatures, and the temperature is divided in two classes, the classes with the invalid values and the classes with valid values. The invalid values correspond to the red areas of the slide before, and these invalid classes are divided in two subclasses. According to the aspect, is it too high or too low? So we have two leaf classes here, the red ones, which correspond to invalid values. Also, the valid values are divided in two subclasses according to the aspect if the ice warning is on or off, and this results in the yellow class here and in the green class here. And the tree would be final, or a good tree from a syntactical view, if we don't have this sign of temperature here below. But I have introduced it because I'm not satisfied with this big yellow class, and I have divided the big yellow class into subclasses. I said drawing the tree is the first step in applying the classification tree method, and the second step is then to actually define test cases, specify test cases, and this is done in something that is called combination table, and this combination table is below the tree, and how it looks in general is depicted on this slide here. You see a very abstract scheme of the classification tree. On top here is the tree itself with the root and the test relevant aspects and the leaf classes and so on. And the leaf classes form the top of the combination table, which is in the lower part, and each line in the combination table specifies a test case, which means we have here 10 test cases because we have 10 lines. And in each line there are some markers, and these markers are set by the user, and these markers specify what should happen in which test case, which means for the first test case here, this means the first test case will take a value from sysleaf class and combine it with a value from sysleaf class and combine it with a value from setleaf class here. And the second test case will also take a value from sys class and combine it with sys class values and a value from set class and so on. I think this is not very understandable, therefore we just go ahead and come to an example, and I would like to show you how I apply the classification tree method to an example, the famous value in range example. And first I give you a formal functional problem specification. This is a blue text which reads a start value and a length define a range of values, and you should find out if another given value is within this defined range or not. The end of the range shall not be inside the range, this is depicted here also. So the end of the range would be this point here, this value here. By the way, we only talk about integer numbers, so we have a clear decision if it's inside or not, and we have not to care about floats or whatever. At this point, I have a question for you, and the question is, how many test cases do you think we need to test an implementation for this functional problem specification? And please give me your opinion by voting. You should see now the three possible answers, and please give me your opinion. What do you think? Not a lot of you are voting, obviously. So I have more or less 50% which are saying no. One thing is, nobody has voted for. Okay, thank you. I close now this vote, and I will show you the results, and you see that most of the people do not think that we need more than 12 test cases. I hide the poll now, and in the following slides or steps I will show you how I apply this method to this problem specification and how many test cases I will think we need. And but keep in mind, this is only one solution to the problem. There could be other solutions, and it is not guaranteed that my solution that I present now is the correct solution or the best solution or whatever. But I will explain my solution, and you can then decide if you think it's good or bad. So let's start. And I said the first step in applying the classification tree method is to find out about the test relevant aspect, which means to make a list of all the things, the items you want to variate during the testing. And for me, for instance, the start value of this range is the first test relevant aspect, because I would like to test with different start values. And the second test relevant aspect, in my opinion, should be the length of the range. For instance, I would like to use a length of 0, and I find it interesting to have also a range with length 0. So therefore the length is also a test relevant aspect for me. And third, it should be clear that we need values which are inside the range, and we need values which are outside the range to get a result of yes and no, which means inside or outside. So the position of the third value is also a test relevant aspect for me. And according to this, I draw the tree, and the initial tree, or my initial tree, looks like this. You see the problem specification at the top, and below the 3 test-relevant aspects I have found: the start of the range, the length of the range, and the position. And I concentrate now on start and length. And the next step would be, which possible values can the start take? And I have now a little bit of a problem. Okay, I know the start value could be all integer numbers, but the problem is that the functional specification does not give me any hint where I should place a boundary for the class. So I need to define such a boundary by myself. This means, for instance, if the problem specification would say if the start value is higher than 20, the length doubles or something like that, I would know that I need a class boundary at the value of 20, but I do not have such information from the functional specification. So I decide to split the possible start values into positive start values and negative start values. And because this equivalence partitioning should be complete in a mathematical sense, I also need to take care of the value 0, and I decide that I make a separate class for the value 0. And with this in mind, I draw the tree, I extend the tree, and my tree then looks like this. I have now the 3 classes that I want to have below this test-relevant aspect range start, and I go now forward. I move on to the length, and because I also do not have an indication from the functional specification to set classes for length, I have put so much effort in defining the classes for the start value, and because it's a systematic method, I would like to take the same classes from the start also for the length. And with this, I can extend my tree, and my tree now looks like this. At the moment, I have only leaf classes. This enables me to define a first test case, to specify a first test case. This is done, or because I do not have the position at the moment, I specify not a complete test case, but only a range that I would like to use in my first test case. And doing this, I need the combination table. I insert a line in the combination table, and I set some markers, and I give this specification a name, and then the whole thing looks like this. The name of the test case I created is trivial, and it combines a positive start value, for instance 5, with a positive length, for instance 2, and this is a range which everyone would have used for testing of this value in range problem. So you could ask, why do I need such a method to specify my test cases? And the answer is, even with this very simple problem and with this very simple classification tree, I am able to define or specify a much more interesting test case, and I will like to show you this test case on the next slide. Maybe you have already an idea. This second test case I have specified has a name interesting, and it combines a negative start value with a negative length. And the question is now, if we have a start value of, for instance, -5 with a length -2, and I would like to know from you if you think, if we test if a value -6 is inside that range or not, if you think the correct answer should be yes, that means -6 is inside a range from -5 to -2, or it should be no, which means it's not inside the range, or that you don't know about this. And I would like to have your answers about, or your opinion about this question in a poll, and I ask you to give me your opinion. What do you think? Start value is -5, length is -2. Is -6 inside correct, or should it be taken as outside? If you would have implemented this problem, what would your software answer? Okay, I already have some answers, but obviously not everyone has a clear opinion, so it's also possible to say I don't know what the correct answer is. So okay, it looks like everybody has voted, so I close the poll, and I will also share this poll with you, and obviously everybody has a clear opinion about yes or no, but you see, almost half of you thinking yes is the correct answer, the other half thinks no is the correct answer. So, and I hide now this poll. Actually, I do not want to know what is the correct answer. The point I would like to make here is that you are not every one of you has the same opinion about the solution of this problem, and actually I also do not know what is the correct answer to this problem, because this is a problem of the specification we have found here by creating test cases. This means what I would like to show here or explain to you is that we have found a problem of the specification by trying to specify test cases for our functional problem specification. And this is the most important thing about the presentation here, that in my opinion, that thinking about test cases is a very good mean to find errors in the specification or omissions or contradictions in the specification. And this is even the case if you do not think by a systematic method about this test case specifications. But the classification tree method is a systematic method that helps you to define test cases, and it's much more likely that you will detect problems of your specification by using a systematic method. And this is the main thing I would like to tell you during this webinar. And please keep this in mind, that thinking about your test cases is a very, very, very important step during testing. And it's much more important to have good test cases than to have a good tool to execute the test cases. Okay, so let's go ahead, go back to the tree. If you are not satisfied with having only one class for all the positive start values, you know that we can iterate the equivalence partitioning method, and for instance we can make two classes out of the positive start values, and I have done this. I have done this according to the size of the values, and I have found two classes for the positive start values. One is called maximal positive, and this is only for one value, and I would like to have this class value to host this class value of the maximum, max int for C programmers, the highest number in the given integer range, and the other class, which is called normal positive, holds all the other values which are positive. And having this tree extended in that way, I'm able to define a third test case, which I think also is interesting, and I will show you this test case here. You see the name of the test case is wraparound, and it combines the highest positive value, the biggest value, with a positive length, and that would mean we have what I call wraparound or an overflow or whatever. And I think it's very interesting to have such a test case which provokes such an overflow, because I find it interesting to see what's happening on wraparound. What about the yellow points here on the left hand side of are they inside the range or not? Nobody knows, because this is not given in the specification. And so we have found another omission of the specification to define what shall happen if an overflow occurs, and so on. Okay, I think we have now a good idea how such a tree is constructed and how the test cases are specified. And I would like to show you now the complete tree which I have created, not with all test cases, just a few test cases. And if you look on the tree, you should see familiar things, like for the start value we have the positive class, and the positive class is divided in one class which is called maximal positive, which only holds one value, and the other normal positive values for the start. And you also see, and this comes now from the systematically of the method, if I had the idea to provoke an overflow in the positive direction, then I should also implement the idea of provoking an overflow in the negative direction. And this is visible here because I have divided the negative start values also into classes. One of them is called maximum negative, and the idea behind this class is that I can combine this class with a negative length and see what happens if I create something like an underflow. And I don't think that you would have this testing idea without such a systematic method. What you also see is I have nothing done additional to the length, but you see that negative lengths are still allowed. We know that the specification does not tell us about the negative lengths and how it should be handled, and one possibility to handle it would be to forbid negative lengths and say, okay, a length is always positive or zero, but never negative. But obviously, I have not extended the specification in that way because we have negative lengths. And you can see with this test case number 5 that I have also extended the specification in a way that I allow values to be inside the range even if the length is negative. This is here because I have a negative length and I have a value which is inside. So this test case specification tells you how I have extended the functional problem specification, and this means a test case specification also is some kind of functional specification. Okay, here's the position. We have neglected the position up to now. You see I have divided the position into two classes. So one class is called inside, where the position is inside the range, and the other answer would be yes, and the other one is outside. And it should be clear, outside needs two test cases. We need an outside test case where the value is below the range, and we need an outside test case where the value is above the range. And this here is the only thing I'm rather strict about. If another tree would miss such a division, the test cases will not be sufficient and complete, and we also will not get sufficient code coverage if we measure it later on. One word about boundary values. The tree would also be okay, syntactically okay, if I would not have this red cluster here, position inside. But I have introduced it to make sure that boundary values are included in the test. And you see it here. I have the position inside, where inside, at the start of the range. This means in test cases here, the start of the range is involved. And also in test cases from this class, where this class is selected, the opposite border of the range is involved. Opposite border means the last value which is inside the range. And boundary values are also involved in outside, where outside, in the class outside, you can see outside, where outside below, and where below, yeah, at the border. So this means if you select this class at a border in a test case, I expect to have the value for the value which is just below the range, the last value which is outside the range. Okay, I think this is clear. On the next page I will show you all the test cases that I have defined for this tree, and I think yeah, you know now that it will be more than 12, but you have no possibility to change your voting. I have found 14 test cases, and the bullets, the markers, say what each test case is supposed to do and which values shall be used. Okay, this is the end of the example. Next I will like to show you how the integration of this CTE works with TESSY, and I have here the tool TESSY already activated. I hope you are a little bit familiar with it. It's based on Eclipse, and you have several perspectives here which are used for the different tasks you take, and I have also made some preparations. I have selected a C-source file and have let TESSY analyze it, and I have one test object in it, which is called isValueInRange. I can give you a quick look at the source code of this test object. So we have here the function isValueInRange. We have two inputs. One is the range, which is a structure. The two components of the structures give the start value and the length, and the return type of this isValueInRange is an enumeration type, which with the two values yes and no. Yes means obviously inside the range, no means outside the range, and yeah, and now we are able to define test cases. Normally we would do this in this perspective test data editor. We could add test cases here, but now we are going to specify this test casing by using the classification tree editor, which is a separate perspective of TESSY. And if I click on this perspective, I see an initial tree, such as the root of a classification tree, and I'm now able to draw a tree, and I will draw a very restricted tree, much smaller tree. I do not need, or I think I do not need the classification for the start values. This means I don't think I want to variate the start value of my test cases, and therefore I don't need a test relevant aspect called start, and I start with the length. So different to what we have seen in the example, we do not have a variation in the start value, but for the length I'm very interested to see how the length 0 works, and therefore I create a class which shall only hold the value 0, and I also create a class which I name positive, and I neglect the possibility of negative length. So I just do not think about this. So I do not need, or do I not introduce a negative class for negative length. What I also need is the position. So I make a classification for position, and I have the two possibilities inside and outside. And as you know, I need a subclassification here because outside I should have two test cases, one where the value is below the range and the other one where the value is above the range or behind. Okay, this is a complete tree. I can arrange it a little bit, and this is I now have accomplished the first step in applying the classification tree method. I have drawn the tree. And I said the second step is to introduce the combination table and have some test cases. But if you use the CTE in conjunction with TESSY, you are able to make an intermediate step. And this intermediate step allows you to assign values to classes. That means every time a class is selected for a test case, the respective value is already defined, and we will see that it is later also present in the test cases. For instance, if I select the class 0 for a test case, I want to be the length of the range 0. Therefore, I introduce this value here. I have on the right-hand side a part of the test data editor of TESSY. And if I select a test case where the length should be positive, I can define here that every test case should have a length of 3, for instance. I could also select another value, for instance 5 or 10 or 100, but I decide for 3. And I can also specify that regardless of the length, I always want to have the start value of the range to be 5. This means this value does not vary. This means all test cases, regardless which length they have, all test cases will have the start value of 5 because I have not made a test relevant aspect for it. And if I go ahead and say every time inside is selected, I expect the return value of my test object to be yes, and every time outside is selected, every time outside is selected, I expect to be the return value of my test object to be no. And having done this, I can proceed with the second step in defining my test cases. I now edit the first line of the combination table. I give the test case a name. I also give it a description. And I set the markers so that I use a positive length and the value should be inside. And by this way, I create some more test cases. The next one I name above, for instance, and I say outside and above as a description. And the length should be positive, and above and below. This means length should be positive and the value should be below, and you might guess it, the last test case is called 0 and it is outside because the length is Okay, now I have finished the test case specification and I can save it, and if I then go to the test data editor, I see the 4 test cases that I have specified inside of the test data editor. Test cases are columns here, and you see in the gray fields there are the values which I have specified in the classification tree editor perspective, and they are taken from there to the test cases. And you see also that I have not specified values for V1, the value which should be in where we want to test if it's inside the range or not. And it's my task now to also fill out the fields for V1. The value that I'm not free to insert any value here, because I need to adhere to the specification, and the specification for test case 1 says the length is positive. Okay, that I have this already with the value 3, and the value should be, the position should be inside. This means, for instance, 6 is a good value for V1 for this test case. In the second test case, the specification says the position should be outside and above. So therefore I select, for instance, 10 as value for V1, or 12, but not 4, for instance, because the value 4 would be a good value for the third test case, where I select, for instance, 4. And in the last and test case I have the length 0, so I could above, for instance, 8 should be good. And now I have completed my test cases. I can save it, and I'm now able to execute these 4 test cases. You see here's a yellow indicator, and if I click on the play button, I will see the test will be executed, and I see all the tests have passed. And I can also see a test report, and we have now the classification tree inside of the test report. So we see in the test report how many test cases we have and what each test case should do. And you see also that the test cases have now names, and they have the specification from the classification tree, and they have the description I typed in the classification tree. And then we additionally see here the values of each test case and if it was failed or not. Just a quick look. And I can tell you that we have 100% MCDC coverage for test cases, and yeah, this should make you a little bit let you think about this, because you know that we have not tested everything, and I can tell you that the implementation had some errors. For instance, if I change this value 8 to 5, you will see that this test case will fail. So it's also possible that values are inside the range even if the length is 0, and we did not test this with these 4 test cases. But on first glance, these test cases look very good, but actually we need much more. So this is a point to think about. Okay, let's go ahead. We have to do some other things. I promise to give you a solution for the dilemma that a developer should not be the tester, and this is shown here, a process which starts with the functional specification of the software unit, and 2 people work on this specification. One person implements the code for this software unit, and the other one specifies test cases according to the classification tree method, for instance. And when both are finished, the test cases are given from one person to the other person, to the tester, and then the tester executes all the tests. And I think this is clear how this should work. And if you think about the case of the negative length, if the implementer has another opinion about the test case -5, -2, -6 as the implementer of the test cases, so this will be revealed, because this test will not pass, and this will reveal the problem of the specification, because 2 persons have thought about this functional specification. And so you could have the efficiency of testing by the tester, by the developer here, by having an independent instance for specifying the test cases. Concluding, you should check the coverage, but I think this is clear. I would, and one thing which supports this process is that you are able to create classification trees outside of TESSY itself. It's possible to have a classification tree here and to have the classification be editor as a separate tool. So you are able to create classification trees without using TESSY, and then you are able to import this classification tree, including the test cases you have specified, into TESSY. And I would like to show you this very quickly. I have here another TESSY module with no test cases for the moment, and I'm able to to import a classification tree from a file, and I need to go to the place where I have this classification tree as a file, and I'm now loading the classification tree in TESSY. And if I save it and if I go to the test data editor, you will see that I have the 14 test cases inserted, and I can but I need to specify test data for it. I think that's clear. But as you know, you see here how the test data should be selected to adhere to the specification of the first test case. I will not go into this deeper. The important thing is that you can divide the specification of the test cases using the CTE. You can divide it from using TESSY. This is the important thing here. Okay, I would like to mention some points, some enhancements. One thing is a mistake I often encounter. Please note that the relation between a classification and a class is not consists of what you see here. You are tempted. People are tempted to make a classification like this and say a car consists of wheel, chassis, and motor, but this is not correct. A car has values like a bus is a car, and a truck is a car, and a passenger car is a car. And so there's a different relationship. If you need something like consists of, you can use an element of a classification tree which is called composition. We have not really introduced this here, but if you recall the is-value in range tree, you will see that we have here a composition made for the range. So it start and length is combined to a composition. So that's the same here for the example with the car. If you need to say a car consists of wheels, chassis, and motor, and then want to see which types of motors are existing, you can use this composition here. Another thing in classification trees are called refinements. Refinements exist for classes and classifications, and these allow you to divide trees and to have a hierarchy of trees. And I will show you an example for such refinements using the tree we had already in use. And if you see here, you see the small is-value in range tree, but you see here on the left-hand side length. The classification length has a double border, and this means there is something beneath this classification, and also the class outside is underlined, which means also there is something beneath this class. And what is beneath? You see, if you double-click on the classification, and we see that there is a classification called length with the two classes we already know is below. And you can go back to the upper level of this tree by clicking on this green arrow, and then we are able to go down to the outside class and see what's below the outside class. Please show here, we simply see in the first test case, the inside class is marked and nothing from the outside class, and in the second to fourth test case, we see outside is marked, but we see not at this level what exactly is marked. To see this, we can also double click on outside, and then we see, okay, the second test case, in the second test case above is marked, and for the last two test cases below is marked. This gives you a possibility to structure your trees, especially if trees are very big. So for this tree here, we would not have the need to introduce refinements, but I just did it for didactical purposes. Okay, so that's about refinements. Another thing I would like to mention is the classification tree method can also specify continuous processes or continuous test cases. You see here, for instance, this is an example about the steering wheel of a car, and this test case here, number 1, says, okay, the test starts in the neutral position, and this position should be for a second, hold for a second, and then the steering wheel should make a right turn, and this position should be held for 3 seconds, and so on and so on. So this is also possible. You see also here a test case can be divided in test steps, like in TESSY, and you can import this also in TESSY. So now I come to the conclusion. I would quickly like to mention some of the benefits I see in the classification tree method. The most important advantage that I see is that the test ideas are visualized, and this makes it easy for someone to review this test cases, and it's rather easy for this reviewer to find out if test cases are missing or if everything is correct or not, especially if you compare it to, for instance, an Excel sheet which is full of numbers and you do not know what a number means, if the 3 is a length or is this a whatever. The other advantage is, okay, it's clear, if you think carefully about your tests, you have more confidence in the tests than otherwise. What we have seen, thinking about the test cases by using the classification tree method can reveal problems of the specification. You divide the problem into smaller ones, so you address complexity, and you also will see how much the test expenditure will be, and you maybe you are able to reduce the test expenditure. Let me close by saying the classification tree method is a guidance for thinking, not a replacement for thinking. Please keep this in mind. We have an additional webinar on this topic on Friday. This one here is more or less finished, and we will have additional webinars on different topics within end of March, beginning of March, for instance. Up to now, the topic is not defined, but if you go to this web page here, you will see which webinars are specified then, and you can register for them. I think beginning of March would be the next webinar series. And if you have any questions about this webinar here or about the classification tree method, you could use the questions window of the webinar tool and write your questions there. Or if you want, you can write me directly an email if you come to questions later on. Please note these two internet address here. This is a main TESSY page, and you can find out current information about TESSY by visiting this site. Especially you see which webinars are announced, and you can register for the webinars or for trainings or whatever. So I'm now at the end of this webinar. I hope you enjoyed it. I hope you learned something which was new to you, and yeah, thank you very much.